Hello again. In our previous videos, we talked through the conceptual overview of the Laplace transform and how we can apply it to process control analysis. We also talked about the properties of the Laplace transform and how we might need to utilize these properties to solve ODEs. Now we're going to work some examples. Seeing things in action always helps to solidify principles. Let's look at a few examples of ODE initial value problems. Here's our first example. It's a first order linear homogeneous ODE and it has an initial value constraint. Okay, this type of ODE you've probably seen before. You're probably thinking, hey, I know how to solve that. I could use separation of variables. I'm very comfortable with that technique. What's the benefit of Laplace transform? Well, as we talked about earlier in the first video, we know that there are properties of the Laplace domain that are really relevant to other aspects of process control. And I think you'll see from working a few examples that this technique is actually just as quick and just as easy as some of those other techniques. And it has a lot more extension into harder and different types of problems. Okay, so how do we start out? Well, when we're solving any ODE, we know that the goal is to solve for y. Here, that's the unknown function, a function of time. Okay, and we know from the ODE that the first derivative of y with respect to time plus 4 times that function y is equal to 0. And the initial value constraint tells us that y at time equals 0 is equal to 2.8. Well, let's go ahead and use Laplace transform to solve it. The first thing we need to do is take the Laplace transform of this ODE. So I put the Laplace transform around this whole ODE, but we know by the linearity property that we could break this up term-wise. So let's do that. First, take the Laplace transform of the first term, okay, plus, remember we can pull out constant coefficients, so 4 times the Laplace transform of y. And this whole thing is equal to the Laplace transform of 0. Okay, so let's work term by term. We know we could use the derivative property of Laplace transforms on this first term. Whenever I'm talking about Laplace transforms, pretty much during the whole course, I will say that the Laplace transform of some variable y, so this whole term, can be represented as capital Y of s. Okay, this will save me a little bit of writing. Okay, so let's rewrite that derivative term. It will come out as s times the Laplace transform of y, so that's capital Y of s, minus the initial value constraint, so that's 2.8, plus 4 times the Laplace transform of y, and all this is equal to the Laplace transform of 0, which is 0. Okay, now let's solve for the explicit form of the function y of s. Okay, here we go. Y of s is equal to 2.8 over s plus 4. All right, so now we're getting close to a solution. We know from basic Laplace transform knowledge that we need to solve for y of t, which is equal to the Laplace inverse transform of y of s. All right? And we know we could find this relationship on a Laplace transform table. So there's some pretty good ones in our textbook. Table 3.1 in our text looks like this. This is an excerpt, the first part of the table. So we can look for something, some function that takes this form. Remember, it looked like this, 2.8 over s plus 4. So what's important to see here? There's a constant in the numerator. There's a constant here in the denominator. Okay, we want to see something in the table that looks similar. And we could see that right here, number 5 looks pretty similar. If we factor out 2.8, which we're allowed to do by the linearity principle, we can see that b would be equal to 4. Okay, so let's do that. we can see that we could factor out 2.8 and take the inverse transform of 1 over s plus 4. All right. From number 5 on the table, we can go directly to a solution. So now we know y as a function of time is 2.8 times e to the negative b times t. Remember that, and here b is 4. So e to the negative 4t. That is our particular solution to this initial value problem. Okay, well that one worked really well for us, and we could see that I doubt you could solve it any faster with a different method like separation of variables. But let's look at one where it's not quite so easy to find the inverse transform. Often that'll be the most difficult part. So in this problem, we see it's still a first order linear ODE, but now it's inhomogeneous, and it's also subject to an initial value constraint. So let's proceed the same way. We'll take the Laplace transform of this whole ODE, and by applying the linearity property, we'll have 5 times the Laplace transform of dy dt, okay, plus 4 times the Laplace transform of y is equal to the Laplace transform of 2. Okay, so taking it term by term, first we'll apply the derivative rule. So this first term is s times the Laplace transform of y, which is capital YS, minus that initial value condition, which is 1, plus 4 times the Laplace transform of y is equal to the Laplace transform of 2. When you have a constant, the Laplace transform of that constant is that constant over s. So in this case, 2 over s. Okay, next we want to solve for the explicit form of this equation y of s. So let's do that. So y of s. So let's see. So first of all, I'll multiply through by 5 and move that constant over here. So we end up with 2 over s plus 5. And then this whole term divided by 5s plus 4. Okay, if you remember in the last problem, at this point we said, okay, now we know there's a relationship between y of t and y of s. All we need to do is find the inverse transform of y of s, and we'll have our solution y of t. Well, that's still true, but unfortunately, manipulating this formula into a form that we can find in our Laplace transform table is not quite as simple. So we'll have to do a little bit of algebraic manipulation to find the solution here. So first thing I usually do is I'll go look at the table and see what's going on. So we see that there'll be, for instance, the function y of s. We can kind of simplify it a little into 2 terms, and we see that it looks more like this. 2 over s times 5s plus 4 plus 5 over 5s plus 4. So the thing that's important to realize is the form it's taking. So we see a constant here in the left term over s times a constant times s plus a constant. And over here in the right term, we see a constant over a constant times s plus another constant. So let's look for familiar forms in our Laplace transform table. Okay, so in this table, we see that number 6 takes the form of that right-hand term, 1 over a constant s plus 1. But keep in mind, look at these. Both of these constants are 1. So we'll need to do a little manipulation to make our functions look that way. Let's keep looking for that other term that included another product with s in the bottom. Oh, look right here. Here, number 13. Okay, here we see the same thing. We see s times a constant times s plus 1 in the denominator. And we see that the constants in the denominator and the numerator are both 1. Okay, so now we've identified that in the Laplace transform table, we can use identity 6 on this term and 13 on the other. Okay, so now what are we going to do? Well, let's factor out the proper terms and to make those constants 1 that we mentioned. Okay, so to do that, I'll rewrite y of s equals, so it should be 2 over 4 times 1 over s times 5/4 s plus 1. Okay, so that's our first term, plus 5 over 4 times 1 over 5/4 s plus 1. All right, very nice. All right, so now we're to the point where we can realize that y of t is equal to 2/4 times the inverse transform of 1 over s tau s, where here tau is 5/4 s plus 1, plus 5/4 times the inverse transform of 1 over tau s, where tau is 5/4 s plus 1. So let's do that for each of these terms. So this one is 2/4. By that table we can see that this inverse transforms to 1 minus e to the negative t over tau. Tau is 5/4. And the other term transforms into 1 over tau, so 1 over 5/4. Oh, look, that's convenient. Those two terms will cancel. E to the negative t over tau. Tau is 5/4. All right, so we can kind of just combine like terms, and we'll find that overall y of t is equal to 0.5 plus 0.5 e to the negative 0.8. That's 4 over 5, the inverse of tau t. That's our solution. All right.